So did anyone think of an idea for the medium problem?
So you sort all the numbers on each computer.
Uh-huh.
Then you find on each computer the highest value and the lowest value.
Yeah.
You compare all the highest values throughout all the computers.
Uh-huh.
And all the lowest values throughout all the computers. Then when you find the highest value in all the computers,
Yeah.
you go value lower on this computer and do the same again. So you walk through all the numbers.
Uh-huh.
And when the highest value is equals the lowest value, you should find the median.
Yeah. If you have a million numbers on each computer, though, this is then quite a time-consuming activity. Yeah, but it's another approach. Yeah. But yeah, I'll let you think about it more because it's, I think, a fun problem. And if you want to get jobs at Google, then it's probably the kind of problem you should be able to come up with an interesting answer for. Not necessarily the most efficient one because no one really cares actually about calculating the median. It's more of, can you think about big problems and come up with good solutions for them? So one of the other things you kind of have to consider is this idea of sort of resource contention, that if you're dealing in parallel or distributed systems, you'll be trying to access a limited pool of resources, and you have to somehow coordinate. So what things get access to which resources at which times. And so actually, most of these tasks are exactly the same when you're dealing with multiple people or multiple computers. You know, if you have a big company and you only have one printer, you somehow have to coordinate who can use the printer at one point. And if someone prints out 20,000 pages and everyone else is waiting to print, then this doesn't work very well. So one of the sort of major problems that comes up with this is this idea of deadlock. And so the typical example of this is the dining philosopher's problem. And so you have 6 philosophers at the table and 6 forks. And everyone wants to eat. And in order to start eating, you need 2 forks, for whatever reason. You then tell all the philosophers to pick up the fork on their left, and then pick up the fork on their right, and then start eating. So all of the philosophers pick up the fork on their left, and then all of the forks are taken, and no one can start eating because no one has 2 forks. And so everyone waits forever for a fork to become available. And so this is exactly what you have happen in computer or parallel systems, particularly in operating systems, where you're waiting for some resource to become available. And because everything is so perfectly synchronized, you end up with everyone having 1 fork, but you don't have enough forks to actually start doing, and so you wait for that to become available, and it never becomes available. And so the only way to really solve this problem, or one of the standard ways to solve this problem, is to kind of jitter things a little bit, where you don't tell them all to do the same thing at the same time. You kind of tell one, okay, grab the fork on your left, the fork on your right, and then start eating. And then a second later, you tell the next one that. And then they're kind of all in a row, and so it's not as much of an issue. It's only when they're perfectly synchronized, which happens when you're on kind of the same core or the same CPU rather than different machines. But it's still kind of problems that come up that you wouldn't have necessarily anticipated until you actually run it. And of course, if you have the dining philosopher's problem and one of your philosophers is a little bit slow, then it's quite possible that that fork is already taken by someone else and someone can actually start eating. And then your problem isn't critical anymore because people can start eating, there's not an issue. It's only critical if they're all exactly kind of the same speed. But the point of this is that you can't really predict always exactly everything that's going to happen. And there's a lot of problems that come up that you wouldn't have anticipated based on your simple problem design. And so another kind of challenge or a set of challenges that you run into are kind of along sort of these 3 categories. So coordination is one of the things we talked about a little bit before, where how do you tell each computer what it should be doing, or each CPU or core what it should be doing, so that it's sort of informed and it's working on a task that contributes to the overall tasks of all the machines. The second is this idea of mutability. And so if you have things that are working on the same image at the same time? How can you be sort of coordinating what's writing to which parts of the image? If you're doing a filter on an image and part of your one core is updating one part of the image, another core is updating another part of the image, and you're using parts of the image that have been updated to calculate your next step, you want to know if it has been updated or not, and so you need to keep track of what's being changed at what point in time. You then have this idea of sort of blocking. And so one of the simpler solutions to coordination and mutability is to say that nothing is allowed to access this image until I'm finished making my changes. But then you lose many of the benefits of parallel processing because you're waiting the entire time for this one core to finish its one task. So distributed computing challenges are then a little bit more complicated. So the first thing is that you actually have to send the instructions and data to another machine. And so when you're all within the same machine in the same program, it's very clear to sort of coordinate different tasks because you don't actually have to send any instructions anywhere. You basically just tell this core, this is what it has to do, this core, this is what it has to do. With distributed computing, you then have to pass messages back and forth. So you have to somehow have machine 1 tell machine 2 what task it has to do. And so how do you send this? How do you make sure the message was received correctly? And how do you make sure that the task that machine 2 does is in fact, when you say sort this list, that it understands that the same way your machine understands that. And so this can become quite messy, particularly if you have different versions or different systems involved. It can be quite challenging to do that. The next is sort of this fault tolerance. And so the idea that if one of your machines starts or crashes or gives a bad result or fails, that the other machines continue running seamlessly, which isn't easy because, of course, if you tell computer 1, sort this list and give me the result, and computer 1 doesn't give you a result, then your entire system waits for that to happen. So that means you need to kind of explicitly say, well, if a result never comes, then try again on computer 1 or try telling computer 2 to do this task. The next on kind of final task is this data storage aspect. And so if you have a parallel file system and you have 30 or 100 machines trying to read at the same time, even sort of the most performant file systems that are around today will be overwhelmed because they can't handle that many requests for huge data sets at the same time. And so unless you can come up with some way of coordinating it well, how many machines are allowed to read at the same time, do you have resources or blocks on this so that you don't overwhelm the file system, and how can you kind of improve that task? So what this ultimately kind of comes down to is that there's really two different ways or two different thoughts you can give for programming and instructing computers or people on what to do. And the first one is imperative. And so that's where you basically give someone a list of exact instructions that they need to follow. And so you say exactly what computer 1 does to which data and how it should do it. And that means that kind of everything is very much sort of explicit what you need to do in what order. And, for making a soup, the example of this would be buy vegetables, then buy meat, then chop carrots, then chop potatoes, then heat water. And so this will take a very long time. And you have no ability, if someone gives you this list, to sort of say, okay, I can have him go buy vegetables, I can have this person go buy meat at the butcher, because these are independent tasks. Because you don't know from this list that that's the case. Because you specified it sort of imperatively, and that doesn't give you any freedom to operate. Because you don't know that maybe you have to go buy vegetables in order to buy meat. There's no way it can know from the beginning that these tasks aren't related. It simply knows these are the tasks and this is the order you give it to. The other approach for this is sort of this declarative approach. And so this is where you focus on goals rather than specific details. And so that means that sort of data is automatically managed and copied, and scheduling is handled by other tools. And so that means for this same soup that your tasks sort of become differently described. So rather than saying this and then this and then this and then this and then this, you say you buy vegetables at the market and then you put that into shop vegetables. You buy meat at the butcher and then you put that into shop meat. Then you can specify dependencies between tasks that are dependent. So, you can't chop carrots into pieces until shop vegetables is completed. And so you kind of specify your dependencies in your hierarchy in the instructions themselves. And so if you think about most of the computer programs you've written, they're much more like this making a soup, where you actually say exactly what task needs to be done in what order, and you wouldn't want the computer to switch the orders of your tasks because it would completely break your system. With the declarative approach, you basically say, this thing is chopped vegetables, and in order to chop carrots, you need that chopped vegetables to be completed. But it has nothing to do with chopped meat, and so that can be done completely independently or by someone else entirely. And so this is a really different way of thinking about problems, but it's important to be able to describe your problems in this way to get the benefits of distributed computing on really large systems. And so, yeah, most languages are much more oriented towards the imperative than the declarative, but with big data and sort of new approaches, things are moving much more in this direction. And if you think about how people operate in systems, at a company, you don't want a boss that micromanages you and tells you exactly what you have to do in what order, because then it doesn't allow you to be creative or to solve the problem in better ways. It kind of forces how you work. You want a boss that sort of says, these are what things you need to get finished. Once you finish this thing, give it to this person so that they can then start on their task. But it allows you to manage your time yourself and to be sort of more intelligent or flexible with this. And so the idea for declarative things is to give computers this freedom as well. And then someone can focus on designing tools that take these list of tasks and perform them in an efficient way. And you can just focus on what the list of tasks that are as important for your problem are. So, they look fairly similar. Kind of the difference, of course, is, if you're trying to make a declarative soup faster or an imperative soup faster, you have no way of breaking this up into separate tasks. It's all one giant task. So if you want to make a bunch of soups at the same time, it's very easy. You could just have people perform this giant task at the same time, but you can't make it go any faster. And with the declarative soup, you can then break it up into separate chunks, and each person can handle one of these chunks. And so, yeah, those are kind of the results that you get, is that the imperative is really optimized for specific tasks. This is the standard kind of cluster-based computing. And declarative is you kind of run everything at once, and you wait for portions to be available, and you have this whole dependency tree set up. And so you deal with things that can happen in the future. And one of the things that's changed recently, or has been changing recently, is that if you have very limited computing resources, you can make imperative programs much more efficient because you exactly handle what each task does, and you can have that very focused and very sort of optimized. With declarative tasks, if you don't have tools which handle that very well, then it will kind of always be less performant than the imperative task. I mean, if you know you're only going to have 5 computers in your cluster, and you want to use these 5 computers as efficiently as possible, then by saying, okay, computer 1 and 2 always read the images first, and then they pass the images to computer 3 and 4, and then computer 3 and 4 do this process, and then they pass it to computer 5, you can make a very efficient sort of pipeline for doing that with an imperative approach. But it takes you a long time to develop this and make sure everything's coordinated well. And what we have now are sort of the ability to get hundreds or thousands of computers very easily. And the task is more, how can you come up with a way of handling all these computers so that you don't have to spend a lot of time coordinating what each one of them is doing. And if it's not 100% efficient, it's not a problem because you can simply add more machines very cheaply. And your time is much more expensive than the computational time. And so this transition is really very closely linked with what computer resources are available. You know, if you have 640 kilobytes of memory, you want to make sure you're using all of them very efficiently. But if you have gigabytes of memory on hundreds of machines, then you don't need to be as sort of detailed with that. Boom. So the second idea that you sort of see with the soup is this idea of lazy evaluation. And so this is where you specify or you run lots of your code where actually nothing's being executed. You're just specifying structure. So how are things linked together? And you only run tasks once they're needed to be run. And so with the imperative soup or whatever that we had before, you sort of buy carrots, peas, and tomatoes at the market. And if you never end up using the tomatoes, you still bought them. With the lazy approach, you don't actually buy the tomatoes until you put them in your soup and show that you use them. And so you can specify lots of things that then are only run or only executed if you need them in your final result. And where this comes in handy is, of course, if you're looking at a huge image data set and you're trying to calculate, how many cells are in the first slice, you don't want your program to load in all of the images for the data set, calculate all the filters and operations on every single image, just to give you the result from the first slice. You want the tool to automatically say, okay, you only need the first slice, so I only need to read in one slice from the input in order to calculate that out. But if you do it in the imperative style, then it will do everything it needs on all of the data and will take forever, and you're only interested in this one slice, and there's no way to communicate to that program that that's what you want to focus on. Of course, you can rewrite it for just one slice, but that's not very efficient. So yeah. And so the idea is that sort of having everything organized well can make this much more efficient. And you want to have tools that make this organization very easy. And you don't want to have to rewrite everything every time you transition from one tool to the next. So to kind of quickly shift over to sort of queue and cluster computing, which is what's available at ETH right now. Basically, you have resources, which are the things we mentioned before, this resource contention, where you have a collection of processors, CPU, GPU, memory, local storage, bandwidth, or like a special resource like a printer. For most clusters, that's not relevant, but that's what's available. And you have each resource for a specific period of time. So when you do cluster computing, you basically say, I need 5 CPUs with 6 gigabytes of memory each for 2 hours. And then the system inside of it, so that's this job, will then schedule your job to run when those resources become available and balance out all of the different people who are trying to submit jobs so that they all get their share of the resources. That if you say you need 1,000 CPUs for 2 months, you'll probably never get scheduled, because if you get scheduled, that means that no one else can do anything on the cluster while this is running. And so the idea of these kind of queue computing systems is that you specify what tasks you need, and then you have some kind of master controller that's looking at all of the jobs that have been submitted and trying to balance the requests of all of the users so that the scheduling is fair. There's, of course, lots of algorithms that can go into this, how you create a fair scheduler. The easiest scheduler is sort of first in, first out, but having one that balances all the different users, or in ETH's case, balancing users that contributed different amounts to the system. So if you come from the computer science department, you have a much higher priority on Euler and Brutus than if you come from the biology department or one of these other ones, because the computer science department has made a much larger contribution to the development of this than the other ones. So the structure of the cluster is that you basically have a master node, and so this is the node that's running on top, which handles all of the other computers in the cluster. So this is the only one that you kind of deal with. The second type is the worker nodes, and so these are all the machines that actually perform the computation, and they're all connected to the master node. And so the master node basically says which machines need to be doing which tasks at what point. And then the scheduler, which is running on the master node typically. And this is where you submit your jobs, and it schedules your jobs to run on different machines at different points in time. And so this tries to balance the resources. This does all of those other tasks. To quickly move through databases. So has everyone here worked with databases before? So SQL or SQL doesn't mean anything. Okay. So a database is basically, so in R or MATLAB or Excel or Python, you kind of have tables. And so a table is kind of, an array with a bunch of column headers in it. And this can handle normal data sets. So if you have a text file or an Excel file and you read in, you can read it in as a table, and you can search through several thousand, maybe up to 1 million different results fairly quickly. But once more than one person wants to be able to look at or change this table at the same time, this is almost impossible in Excel or any of these other tools. You can't have a MATLAB table shared between multiple different computers where people are making changes to it at the same time. It simply doesn't work. So if you're dealing with something like a table full of customers or a table of results that a bunch of people are looking at and changing, you can't have that as one file on one computer. And so that's where this idea of kind of databases came from, that you have tables that are shared between many different computers, and you have a specific way of storing these tables and getting information from them and putting information into them. And so that's what this SQL language stands for. And so this is structured query language, and it's a sort of commonly accepted format for reading information and putting information into tables like this. And so when you read into a table in MATLAB, you sort of say, these are what the different columns are. If you want to add a column, then you add a column to your matrix and you put it in there. But you then have, if someone else opened this table on another computer and they used R to look at this text file, they would use a completely different command to add a column to this data frame. And with SQL, everyone has exactly the same set of commands that they use, and so it doesn't matter what tool you're using. You sort of have a common infrastructure or a common language for communicating changes and updates to this table. So here's kind of a simple example where you have two tables with maybe like experimental results. So the first one might be your animals, where you have an ID column, which sort of specifies what ID this animal has, and then some information about the animal itself. And so in this case, it's weight. And so you have animals 1, 2, and 3, and weight 140 and 80. You then might have information you've done for each one of these animals, like a table full of cells. And so if you did experiments on each one of these animals and looked at the cells that they had, you might have a cell table where the first column tells you which animal this cell was taken from. The second column kind of says if it's a cancer cell or a healthy cell, and then maybe you have some of these sort of standard metrics that we looked at. And so the structure of this is then a relational database, because you have a database here of animals, and you have a database here of cells, and they're linked together. So this animal ID here has to map to one of these IDs there. And so this whole idea of relational databases is that you can store pretty complicated structures or hierarchical information, like different cells for different animals, by having these links between multiple different tables. So you could also have another table here of organs that described different organs inside these animals. You could then have a table above animals that had information on sort of groups of animals that you were looking at, or maybe a table of mice and rats that sort of had what species they were or something like that. But that basically you end up with the ability to express very complicated information with fairly simple structures that everyone's able to agree on, and you can use one common language for looking and analyzing these kind of data sets. And so if you visually look at that, you sort of have this table, this is the animal table, and this is the cells table, and you have these columns that are sort of related to each other, and that's this relational aspect of the database. This structured query language is how you actually analyze it. And so if you want to get the volume of all the cells, you run a command like select volume from cells. And so that's what SQL looks like. You then send this command to your SQL server or whatever tool is running this or hosting this. It then gives you back sort of this array with all of the different volumes of the cells that you have in your database. You can then do more complicated things, like say you want the average volume of the cells that have cancer, and you specify the query like this. And so it allows you to sort of do fairly complicated things with your data set. This is just the very basic commands that are available, but these get much more complicated without actually having to worry about what your data looks like, how it's being stored, how many computers the data set's distributed across. And so this is kind of the first example we have of kind of a declarative language. And so you don't tell it how it calculates the average or how it should, sort of partition the data or read data from different partitions. You simply say you want to get the average volume from all cells that meet this criteria. How it goes about calculating that, you don't care at all. You just want to get the result at the end. And so this can be, one process running on your machine. So in the case of SQLite, you can use a database as sort of part of your program. And so like Firefox uses SQLite for managing bookmarks. Many websites use SQLite internally for keeping track of sort of, login information or passwords or things like this. Or this could be a cluster with 10,000 machines on it, with the data distributed from hundreds and millions of cells. And this query looks exactly the same, but the execution of this query can be very, very different. And so this language is probably one of the most important programming languages to know for working in data science, because it's the standard that's kind of used for all standard data. So what big data is talking about is not when MATLAB runs out of memory. Big data is talking about when SQL databases don't scale well anymore. And so that's kind of where all of these tools come from. And SQL databases are what insurance companies use to keep track of hundreds of millions of properties all over the world. And, who owns them, what sort of claims need to be paid, what customers have paid their bills, which ones haven't, That's what standard data is. Big data is when you have so much data that you can't use those tools anymore. And so I think particularly for scientists coming from the background of, MATLAB and R and C++, big data isn't when those tools are full. Big data is when these databases, which run already on dozens of different machines, stop scaling well. So here's sort of examples of more advanced SQL things you can do, that you can sort of make subtables or views on tables. So you can then make a subtable where it's just the animals where the weight is above 80. And then you can run a query on that to get the volume of the cells. So you can kind of link these things together. You can also get weight and average cell volume for all the mice. And so you can sort of join these tables together, and instead of focusing on just the animals or just the cells, you can kind of link them and look at both of these pieces of information at the same time. And so here again, you see you have very complicated ways of combining these data, but you don't say at all how this task needs to be performed. You don't say read in this index and then take this index and this other one and copy it there. You simply say this is the result that I want to get. The database server should figure out the most efficient way to read in these tables and process this data together. So yeah, you can also express things like networks using SQL. And so if you have sort of a table representation of a network where, if you have cell 1 and cell 2, you can then, measure the number of junctions or the strength of the connection between them. And so you can come up with the number of connections each cell has to each other cell. So this is useful for things like the distribution metrics we talked about, where you come up with sort of the links for all the different objects in your system, and you want to understand how they're all connected together. That you can use SQL tables for calculating things like this on very, very large sets of data. Beyond SQL, so SQL is already kind of at the limits for many of the new problems that exist today. And so if you look at sites like LinkedIn or Facebook that make suggestions for who your new friends or new contacts should be, some of the tasks that they're doing are looking at these graphs and trying to find out people who have very similar friendship graphs as you or have many overlapping elements in these graphs, and then suggesting people that might be your friends based on the friends that you kind of have in common. And so if you look at queries like this, you can do these kind of queries in SQL, but they can become complicated very quickly. And so if you think about a site like Facebook that has, I think, over 1 billion users, then you're trying to look at graphs with billions of elements in them and trying to find kind of links or jumping across many different elements of this. And this can be then a very, very complicated query to execute. And so you want databases that are better suited for handling those kind of problems. And so you have this whole sector of graph databases, which are just focused on looking at connections between people or connections between cells or objects and making queries on them very simple. Because this query is, how many cells are within 2 connections of each cell. And if you wanted to go 3, 4, 5, n, then you'd have to make this query longer and longer to handle that. And with a graph database, you then have a specific structure for making a query that goes across n of these different connections without manually writing this all together. So with SQL, as we have it here, this scales then quite well to millions or billions of people. It then just doesn't scale well to more complicated types of queries. And that's where you need these new kind of approaches, and this is also kind of associated with the big data movement, because the SQL language is very good at handling sort of these relational databases, but it's very poor at expressing graph or complicated graph structures. If you wanted to make Google Maps with a SQL database as the backend that had all of the roads in the world and which roads are connected to which other roads, to write a query on a SQL database that would give you the most efficient route would be very difficult. And with a graph database, this is sort of a built-in tool because it's designed just for those kind of tasks. So for big data definitions, kind of the first aspect of this is this idea of sort of velocity, volume, and variety. And so where you have a lot of data, sort of the volume aspect, so you have a huge amount of data that needs to be processed. Where you have data coming in very quickly, and so like with SQL, as we mentioned before, you can deal with millions or hundreds of millions of rows inside your SQL database, but when you perform complicated queries, so if you were to perform a query like this on the Facebook database of all the users at Facebook, without using any big data approaches, it would probably take several hours or days even to calculate that one query. And so if you're trying to make this query as part of a website, that means you need to have a result in 100 milliseconds. And so clearly you need a different approach for dealing with this kind of scale. And then finally, variety. And so that's where your problems aren't always really well structured. So when we talked about the SQL databases, that you sort of have columns that are